Hi, my name is Chris Jericho Jew, and I'm going to present about the introduction. The purpose of the Australian built the bridge is to connect Sydney city centre with the North Shore for easy transportation. The construction began in 1924 and it took 8 years to build, and the official opening was on March 19, 1932, and it was designed by the British engineering firm Dorman Long, and the material they used was 53,000 tons of steel and required thousands of workers. The challenges was workers had no safety equipment, making it a risky job. And the record is when completed, it was the world's largest steel arch bridge. And it became a global symbol of Sydney and Australian innovation. The nickname known locally as the coat hanger because of its arc shape. The cultural importance is a historic landmark and a centerpiece of Sydney's New Year's Eve celebration.
Hello, Assalamualaikum Doctor. My name is Muhammad Hijazul Razin. Today I want to share about literature review of my team project. So the Sydney Harbour Bridge, complete in 1932, is considered one of the greatest engineering feats of the 20th century as one of the largest steel arch bridges in the world. It plays an important role in the study of statics, material science, and structural engineering. This review will focus on various studies related to the force acting on the bridge, its design, the material used, and ongoing evolutions. So next for material selection, steel was crucial for the Sydney Harbour Bridge as its excellent strength to weight ratio allowed it to support massive forces from the long span and dynamic loads. Steel and compression, the bridge strength released on steel in the arch and deck as it excelled under compression, efficiently transferring roadway loads to the support and minimizing tension and bending. Reinforcers concentrate the piers and pylon made for reinforced concentrate provide strength and stability, effectively transferring larger force from the arch to the ground. Corrosion resistance located in a coastal environment, the bridge is required protective coating and anti-corrosion paints to prevent steel rusting from the salt water, ensuring its long-term preservation. So, there is for structures analysis. Specification structures of Sydney Harbour Bridge. Length of the bridge was 1,149 meters. Main span 503 meters. Pylon height 134 meters. Arch height 132 meters above sea level. Deck width 49 meters. Steel weight over 52,000 tons. Number of rivets more than 6 million. Next, for structural behavior, we got static loads and structural response, dead load, safe weight, calculation method, life load, trains, and lastly, wind load. So next, as we can see, there is methodology of this project. The main design idea was the parabolic arch was chosen to effectively carry the compression forces. Early static design aimed to minimize bending and shear forces to keep the bridge stable. Early static studies, models such as Castigliano's theorem and Euler-Bernoulli beam theory predicted the response of the bridge under various load, considering forces along the arch from top to support, even in extreme conditions.
Sydney Harbour Bridge Challenges and Solutions. The Sydney Harbour Bridge is an iconic landmark and a vital part of Sydney's infrastructure. It connects the city's central business district to the northern suburbs, supporting vehicles, trains, and pedestrians daily. However, it faces several challenges that must be addressed to ensure its long-term safety and functionality. First, structural integrity and load capacity problems. Increasing traffic and heavy load strain the bridge, which was originally designed for lighter use. The impact on that is material fatigue, cracks, and corrosion risk. The long-term stability of the bridge. Second, corrosion and material degradation problem. The salty environment causes corrosion of steel components, and the impact is weakening of the structure and potential failure of critical parts. Number 3 is traffic congestions and capacity limits problem. The bridge often faces severe traffic congestion, especially at peak hours, and the impacts it causes delays, increased pollution, and inefficiency in Sydney's transportation network. Number 4 is aging infrastructure and maintenance. The problem is it is built in 1932. The bridge requires regular maintenance to prevent failures, and the impact is it's been delayed repairs to disrupt traffic, tourism, and daily life. Number 5, vibration and dynamic loads problem. And high-speed traffic, trains, and strong winds generate vibration that can cause stress for the structure, and the impact is long-term exposure can cause fatigue and deformation. And number 6 is seismic and environmental risk problem. While not in a high-risk earthquake zone, the bridge faces risk from seismic activities and extreme weather events, and the impacts it will potentially leave structural damage and disrupting transportation and daily life. In conclusion, the Sydney Harbour Bridge is an engineering marvel and critical part of Sydney's economy and identity. They need to have regular maintenance and monitoring, traffic management improvements, investment in new technologies to strengthen the structure, and by addressing these challenges, we can preserve this landmark for future generations.
The Harbour Bridge is a complex structure with several interacting components, including its arch, deck, supports, and foundations. In engineering, the behavior of such a bridge can be analyzed using various of mathematical models to describe the forces acting on it, its structural deformation, and overall stability. Geometry. Parabolic curve. The Sydney Harbour Bridge uses the parabolic arc as its main structural components. The shape of the arc can be mathematically described by the equation of parabola in a coordinate system where x-axis runs along the length of the bridge and the y-axis represents height. The general equation of a parabola is y equals to ax with the power of 2 plus bx plus c, with y is the vertical positions of the points on the arc, x is the position that along the length of the arc. A, B, and C is constant, determined based on the geometry of the bridge. Given that the arc is symmetric, the equation simplifies as y equal to ax with the power of 2 plus c, where a is related to the arc's curvature and c represents the height of the apex at the arc, which is the topmost of the arc. Number 2 is static load analysis. The forces acting on the bridge, such as dead load, live load, and wind load, can be represented using principles of statics. To calculate the internal forces such as compressions and shear at different points along the bridge. Dead load or self-weight. The total weight of the bridge is calculated by summing the contribution of each components. W total is equal to summation of Wi. W total is the total weight of the bridge. Wi is the weight of the components such as steel arc, deck, piers, and etc. The total force due to dead load acting on the bridge can be used to calculate internal forces such as compression and shear at different points of the bridge. Live load. The live load caused by vehicles and pedestrians can be represented as a distributed load over the length of the bridge. The equation for the distributed live load Qx along the length of the bridge can be written as Qx equal to P live L, where Qx is the load per unit length of a point at X. P live is the total live load. L is the total length of the span. The live load distribution can be used to calculate the resulting internal forces and stresses at various points of the bridge. Lastly is wind load. Wind load acting on the bridge is calculated using aeroanalytic analysis. A simplified model assumes that wind generates a uniform force per unit area of the structure, which can be expressed by F wind equal to 2 times rho times CD times A times V. F wind is the wind force, rho is the air density, typically in 1.225 meter per second, 1.225 kilogram per meter square at sea level. CD is the drag coefficient depending on the shape of the bridge. A is the cross-sectional area of the bridge exposed to the wind. And lastly, V is the wind speed.
Hi, Assalamualaikum. My name is Muhammad Kibran Hakim. My number metric is CD240223. So today I want to explain about result and discussion for our project is the Sydney Harbour Bridge. So for the result and discussion, we go to result first. So for the result, we must do for this case, we have to divide into a smaller section for this bridge, because this bridge is very bigger and longer, so we have to divide into a smaller section. And because we have to analyze the force acting on them, so we have to use a method of section for find the force acting on the bridge. And the second, we have to use trusses to cutting a part of truss in the bridge, on the bridge. So we have a procedure or step to find the force acting on them and cutting part of them. So for the first step is we have to define which part we have to cut, and second we have to separate them to the section, and third we have to solving using we have solve using a static equilibrium equation. Like we have three unknowns, summation of fx equal to 0, summation of fy equal to 0, and summation of moment equal to 0. So we move into the equation. So first we have to determine the force. Like we have to find the support relation to a 2 point, like in the example FBD, or my FBD that I have, that I drawing. So we have a 2 point in the bridge, have a pin and a roller. So the pin, we have know that the pin can moving into the x-axis and y-axis. So we have to put the x and xy, because in that case point A have a pin, so then they can moving into the x-axis and y-axis point lah. So into the K point is roller can moving in the y-axis but can move into the x-axis, so we have to put the y. So the case is we have to put the ky in that force. And first we have to draw a FD diagram, and second we have to calculate the moment fx and fy. So first we have to calculate the moment. We have to put the we have to define the moment at the point A, because point A have x and xy. So we using a moment at the point A, and you have to calculate and get the ky. So the answer for the ky is 202.5 kilonewton, and that we know that they're negative. So the negative, we have to put the compression for that case. And for the fx, summation of fx is equal to 0, and we have to find the ax for this case, because have the force acting on ax axis. So the ax is equal to 50 kilonewton. So that is tension, and summation of fy equals to 0, and we get the ay. So ay is 0 kilonewton, and that is tension too. So for the next, we moving to the next expression. So we have to find the truss member, the which part we cut. So we decide to cut the part at the point C and D. So for the first, we do the same thing. We have to draw a FBD, so we can get clearly that we have to find the force at the point that we want to know. So first we have to do a summation of moment at the point C. So we using a point C as a moment that we have to find. So summation of moment at the C equal to 0. So we can get the FBD of or BD, force at BD. So we get the 680 kilonewton, and then is tension. So second, we find the FBC, summation of Fy equal to 0. So we can get the FBC equal to 825.70 77 67 kilonewton, and then is tension, and the next is Fx equals to 0, summation of Fx equal to 0. So we can get the FCAO point AC. So the FCA is 1200 10.73 kilonewton. So the FCA is negative, so we get the compression of this part of the force. So just it for analyze the force at the point that which part we currently. So for this discussion for this case of Sydney Harbour Bridge, so the Sydney Harbour Bridge integrity is assessed by calculating the lift and dynamic loads, and ensuring the arcs can safety carry traffic and environmental stress. So the design focus on the compression and bending and tension force for the stability for this Sydney Harbour Bridge, and for the regular maintenance and uploaded calculation, the regular maintenance and updated calculation ensure its safety and durability in handles heavy traffic.
Conclusion: the Sydney Harbour Bridge is a great example of how we use the basic of mechanics to build something strong and safe. The big arc works by spreading the weight of the bridge, cars, and the people to the strong end called abutments. This balance of forces keep the bridge steady and stop it from falling down. Engineers planned carefully to make sure the bridge could handle heavy loads, strong winds, and even changes in temperature. They used strong steel and smart design to make it last for many years. In simple terms, Sydney Harbour Bridge shows how understanding and using the basic of balance and strength can create something that's not just useful but also amazing to look at. It's a bridge that works and lasts because the forces on it are perfectly balanced. And that's it from me. Thank you.